Okay, today we're going to talk about the mean value theorem, but before we do that, let's do a quick review of Rolle's theorem and compare and contrast the differences between these. So Rolle's theorem said f is a continuous function on a closed interval from a to b, and it's differentiable on the open interval from a to b. If, and here was the key for Rolle's theorem, if f of a is equal to f of b, then there's at least some number, c, in that interval, such that the derivative is going to equal 0. And I like to look at this graphically. Here we plug in our a value and we're mapped to the function and over to the y-axis, and we're at our f of a is at this height. And the same thing for the other endpoint. The right endpoint goes into the function, gets mapped over to the y-axis, and we have the situation that f of a and f of b are equal. And the Rolle's theorem guarantees we're going to have some interior point with a derivative equal to 0, which means there's going to be a horizontal tangent line at that point. And it's also key to note here, if I look at the endpoints, here's a, comma, f of a, b, comma, f of b. If I draw a line through those endpoints, draw a secant line through there, this secant line through the endpoints and the tangent line at our point up here are parallel. They share the same slope. Now, that is Rolle's theorem again. The mean value theorem is just going to sort of tilt this picture. So here's the mean value theorem. Rolle's theorem can be used to prove this other theorem, the MVT. So this theorem states if f is continuous on the closed interval a to b and it's differentiable on the open interval a to b, just like Rolle's theorem, now it says there exists a number c in that interval such that the derivative at point c is equal to this, f of b minus f of a over b minus a. And if we go back to the picture and look at this, you know, here is our b value goes in. F of b is this point on the function, bf of b. If we plug our endpoint a in, we're mapped up to the function here. And this should look vaguely familiar from algebra classes in the past. It's just the slope that's occurring between these 2 points. So if I connect these endpoints of the interval again through a secant line, in Rolle's theorem, we took the derivative and set that derivative equal to 0 for a horizontal tangent line. Because now f of a and f of b are no longer equal, we cannot be guaranteed a horizontal line in somewhere in that interval. But what we can have is a tangent line to our curve that is parallel to the secant line through the endpoints. So when we were doing Rolle's theorem problems, we would take the derivative and set that derivative equal to 0. So our tangent line would be parallel to the secant line through the endpoints a and b. We're going to do the same thing here. Now we're going to take our derivative and not set our derivative equal to 0. We're going to set the derivative equal to the slope of this secant line through the endpoints. Now you can read that on your own. And here in example 3. It says here's our given function, 5 minus 4 divided by x. Find all values of c in the open interval from 1 to 4, such that the derivative at point c is equal to this. And again, this is just the slope occurring through the secant, or the slope of the secant line going through our endpoints. Again, here in our picture, let's just work on our function. Here's f of x. It's equal to 5 minus 4 over x. And I want to check out the height at my x values. So the first thing I'm going to do is plug in my first left endpoint x value, f of 1. If I plug a 1 in for this x, I'm going to have 4 divided by 1 is 4, and 5 minus 4 is 1. So I know the coordinates of my left endpoint, 1, 1. And now I plug in my other endpoint, x value of 4. F of 4 is equal to, I plug a 4 in for this x, 4 divided by 4 is 1, 5 minus 4 is 4. I plug a 4 in for this x, 4 divided by 4 is 1, 5 minus 4 is 4. So there's my other endpoint, 4, 4. Now I want to find the slope that's occurring between these endpoints. Graphically, here's our endpoints. We want the slope of this secant line. So again, slope is y2 minus y1 over x2 minus x1. I just subtract my y values, 4 minus 1. Divide that by subtracting my x values, 4 minus 1. So when I subtract, I get 3 over 3, or 1. The slope of this secant line is equal to 1. M equals 1. Now I'm going to take the derivative of my original function and set my derivative not equal to 0, like in Rolle's theorem, but I'm going to set it equal to this secant line's slope of 1. So again, here is our original function, 5 minus 4 divided by x. And I'm going to take the derivative, f prime, of x. And it's easier to think about this as 5 minus 4x to the negative 1. Bring that x up, change its exponent to a negative. So now when I take the derivative of this constant is nothing. Taking the derivative of negative 4x to the negative first power, I'm going to get 4x to the negative 2 power. And to get rid of that negative exponent, I just move it to the denominator, 4 over x squared. Now, again, in a Rolle's theorem problem, we'd take this derivative, set it equal to 0, because our tangent line would be horizontal and therefore parallel to the secant line between the endpoints. But now our endpoints are not equal. F of A is not equal to F of B. So I'm going to take this derivative, and I'm going to set it equal to the slope we found between the endpoints, 1. And I'm going to solve for x. First, multiply each side by x squared. 4 equals x squared. To find x, I take the root of each side, and I'm going to have x is equal to plus or minus 4, positive or negative 4. But again, we go back to our interval. No, what am I thinking? The square root of 4 is 2, plus or minus 2. And this 2 is the x value occurring below the point where our tangent line has that slope of 1. Again, we had a plus and minus 2, but again, our interval is restricted 1 to 4. So we can eliminate that negative 2 possibility. And if we did want to find the actual point of tangency, we would take this x value of 2 and plug it into our original function. Plug a 2 in here, we'd get 4 divided by 2 is 2, 5 minus 2 is 3. 2 comma 3 is the exact point where our tangent line touches the curve, and they share that slope of 1. Okay, here in example 4, we have 2 stationary patrol cars equipped with radar 5 miles apart on a highway, as shown in the figure. As a truck passes the first car, its speed is clocked at 55 miles an hour. 4 minutes later, when the truck passes the second patrol car, it's clocked at 50. Prove that the truck must have exceeded the speed limit of 55 miles an hour sometime during the 4 minutes it was in between these 2 squad cars. Now, we don't have a function that actually describes the speed of the truck over the interval, but what we can do is take the endpoints of the interval, find the slope going through them, and we know by the mean value theorem that there's going to be at least one point in there that we're going to have that same value. So, this problem starts when the truck goes by the first car. So at the first car, time is equal to 0. First car, t is equal to 0. That's when the problem begins. At time 0, the first officer hits the truck with the radar gun. The second car, when do we pass the second car? At what time? Well, we're talking miles per hour here, and we have everything else in minutes, so let's convert to hours. 4 minutes is 4 minutes out of a 60-minute hour, or 1/15 of an hour. So for the second car, t is equal to 1/15. And we'll use s of t as our function. Our function is s for time t, and that's just going to be the distance traveled by the truck. Distance traveled by the truck. Okay, so let's find the endpoints of this interval. So s of 0, when the problem begins and the truck is passing the first squad car, time is 0, and as far as the problem is concerned, we've traveled a distance of 0 miles. So s of 0 is 0, or the left endpoint of the interval is 0, 0. S of 1/15. Again, S is the function for how far the distance or the truck has traveled. S of 1/15, we've gone 5 miles. It was given in the setup of the problem. So our other point is 1/15, comma 5. Now we want to find the slope occurring between these endpoints. So we're going to do the y values subtracted. The numerator of the slope formula is y minus y, or I'm going to go 5 minus 0. And the denominator is the change in the x values, 1/15 minus 0. So we have 5 divided by a 15th, or we can invert and multiply, and we're going to find that the slope of the secant line going in between those endpoints is 75. 75, and that'll be in miles per hour. Again, we don't know if we had an xy axis. We do not know what the function would be that would describe the truck going across that interval, but we do know the endpoints. The secant line, where is that? The secant line between the endpoints at the beginning when the first police officer clocked him and between the second one, we know that that changed at 75 miles per hour. Again, we don't know what the function looks like, but we do know that we're guaranteed by the mean value theorem that there is one point somewhere in that interval that the truck was traveling at least at 75 miles per hour. And then there's also a useful alternative to this mean value theorem. If f is continuous on the closed interval a to b, differentiable on the open interval a to b, there's a number c somewhere in that interval such that f of b is equal to f of a plus the quantity b minus a times the derivative at point c. Keep in mind when we're doing the problems for this section that all polynomial functions, rational functions, and trig functions, they are differentiable at all points in their domain.